Okay, here we are back for homework number 2. So I know we're gonna have a little bit of time in class before I end up leaving. So it's gonna be, 2 or 3 days in class, and then I'll be gone for 2 weeks. So again, that's why I'm doing these videos. Please take the time to watch them. Again, you're not having to come to class the 2 weeks that I'm gone. So it's up to you to make sure that you watch the videos and get the help that you need. So what we're going to do right now is I'm going to share my screen. This is again our OneNote. So this is what it looks like. These are all the topics that we're going to go over, and we already did review topic 1. And in the Canvas class in module 1, if you scroll to the bottom of the module, you'll see OneNote link, and then you'll see OneNote lecture for homework 1, and then this one will be for homework 2. So I also have embedded the documents that I'm working on. So these would be the documents that I would hand out in class. If I don't get them handed out to you before I leave, this is where you can get them. So you can get them here. You can click on either of these links. They're the same thing. One's in PDF and one's in Word document form. So either one, you'll get the same information. Or there's a link where the videos are. There's also a link with the document. So in your Canvas module 1, so you can get your information from there too. So let's see. Okay, so what we're going to do today is we're going to kind of talk about the big difference between let me share the screen here. That might be super helpful. The big difference between algebra and calculus. So algebra is very specific. For instance, when you are reading something that looks like this, so if you see some functional notation that looks at that, what this is saying is, what is the y value when x is 3? So if we were looking at a graph, let me get a graph here. If we were looking at a graph here, okay, and obviously this is 0, 1, 2, 3. So this is our x-axis, and here's our y-axis. And let's say our f function. So again, that's why we use functional notation, because we can look at it and go, oh, okay, this is talking about the f function. So if I had an f function of f of x equals x, and then over here, let's say I had a g function that g of x is x squared. Well, just the functional notation of f of 3 tells me, okay, we're only using the f function, and what it's saying is, when I replace x with 3, what is my y value? So if I put 3 right in here, I get 3. So the value is very specific. So at x is 3, y is also 3. So that's super specific. It's one individual point. That's it. We're only looking at a very specific value. If over here I said, what is the value of the g function when x is 1? Well, I find my g function. My g function is x squared. I plug in a 1. 1 squared is 1. Okay, so I'm looking at a very, very specific point. What you guys are used to seeing it as is ordered pairs. When x is 3, y is 3. On the g function, when x is 1, y is 1. And again, this just happens to be, the same value. It doesn't always end up like that. So for instance, if I said, if x was 2, y would be 2 squared, which is 4. So your ordered pair would be 2, 4. So the value of y is all determined by the value of x. So you plug in an x, it spits out a y. Okay, so that's the idea of a function. So the difference between algebra and calculus is, now calculus, we get to kind of open up the picture a little bit, And we get to see, oh, what's going on around the point. So for instance, if we were looking at this this graph, let me erase some of this stuff. Sorry. I haven't used this in about 1.5 years, so I have to remember how to use it all. So if we were looking at this graph, and let's say now we have a value here, but it's an open circle. So remember, closed means the value exists there, that there is a value at that point. When you have an open circle, it means there's no value there. So when x is 3, there's nothing going on there. But with calculus, we can look around the function and go, oh, but what's going on around it? So if this was our function f of x, right, now it's a completely different function. It's not just x is 0 anymore, or f of x equals 0 anymore. Now it's a much more complex function. We can say that at x is 3, there's nothing going on. But man, we can look all the way around it and figure out what's going on as it approaches 3. So it's a huge difference. It's not the algebra question of what is going on at that point. Now we're looking at the calculus question of what's going on around the point. And so with how this works with business is this could be a graph of a business profit, right? Where the profit goes, it was going up and then it went down, and then boy, it really boosted, and then something happened right at, say, the 3-year mark, if this was in years, right at the 3-year mark where nothing was going on, there was no business happening, and then something happened and then it took off again, and then it kind of, the profit kind of flattened out, and maybe even we lost a little bit. But in business, it's not just a straight line. You're going to have highs, you're going to have lows, you're going to have stuff where, you know, like during the pandemic when nothing was happening for a lot of the restaurants and businesses around the world, really. So now we can look at through the lens of calculus and go, okay, what's going on around it? What happened right at that 3-year mark where nothing was going on? So that's the big difference between algebra and calculus. Algebra is all about what's happening at a very specific point. There's no question. It's just, you know, when we have 10 products, we make a revenue of, you know, $30, or at year 7, we know exactly how much money we had to, you know, spend in order to keep the business afloat. Where calculus, we can look at and see all the stuff that's going on around that function. And so it really does open up a lot of windows for us to be able to look a little bit deeper into what's going on around in our business world. So that whole concept of what's going on around a particular point is called a limit, L-I-M-I-T. So that's that idea of what is a limit. So a limit is, what is the value as we're getting towards 3? So for instance, with this graph right here, we're looking at it and we're going, okay, we can see from this side, we can see from the left side that if I follow the graph with the orange, I can see as I get towards x is 3, I'm heading towards y is 3, right? If I'm coming in from the right side, my graph's a little bit different, but I'm still heading towards the same value of y equals 3. So the idea of a limit is, and if you can see my fingers, the idea of a limit is, what is the graph heading towards? And are my fingers coming together at that point? Or is one finger going up and the other finger going down? And at a certain point, my fingers are at 2 completely different places. So limits, you have to kind of change the way you think. It's not what's happening at the value, because with this graph at 3, there's no value there. It's an open circle. But we know what's going on around the value. And so if we know what's going on around the value, and getting really, really close to the value, we can kind of identify, okay, what's happening at that point. Okay, so let me scroll down a little bit. So this is the math part, so with calculus, you have to be able to read math and understand math language, but I'll try to take the math language and put it into just common, everyday language. I'm much better at that. Okay, so the limit of a function, this is the definition. The limit of a function, and so there's some new notation that you have to be able to read. So this LIM means limit. F of X is your function, could be G of X, could be H of X, doesn't matter. It's just whatever that function is. As X, so I'm reading right here, as X approaches some value called C, then the limit is L, because it's approaching a certain value. Okay, so that's how you would read this. The limit as X approaches C of the F function is L. If the functional values of the F function is close to the single real number L, whenever X is close to but not equal to C on either side of C. So here's what this means. When you look at this graph, you can see that our values, both sides, so think of my right hand is coming in from the right, my left hand is coming in from the left, but both fingers are coming to this point, get my pen to work here, this point right here. That's where my fingers are heading towards, okay? It's heading towards that value, and that value is 3. That's the L, that's that capital L, that's the limit. So as you're reading, a limit will always equal the Y value. Okay, where our fingers are coming to, that's what the limit is always going to equal, the Y value. Okay. All right, so that's the math part of it. So this first part, I'm going to kind of, I'm going to kind of go over a little bit, but it tells you how to read it. The limit of F of X as X approaches C is L. Okay, what that means is it's getting arbitrarily close to the value, and the value C is just any value, a constant. You can think that as it gets closer and closer and closer, it's getting closer and closer and closer to whatever that Y value is. Okay, so this is important. The existence of a limit at C has nothing to do with the value at C. Okay, the existence of a limit at C has nothing to do with the value at C. It's possible that C won't even be in the domain. So remember, domain is what are the values that X can be. So that's this graph is a really good example. The limit has nothing to do with the value at C, because in this example, the value at X is 3 doesn't exist. It's an open circle. But we know what's going on around it and what is it heading towards. Okay, so you're going to see me use my fingers a lot, because every time my fingers come together, the limit exists there. If my fingers do not come together, they come to 2 different places, now there is no limit. Okay, the limit does not exist, and I'll show you some examples of those. Okay, so we're going to start, this is just a graph of this function, this F of X function here. It's showing asymptotes. Asymptotes are vertical lines that are kind of like a invisible wall where your graph approaches it, but it can't cross it. An asymptote can also be a horizontal line where your graph approaches it but doesn't cross it, and so on. So let's get to this example too. I think this will make much more sense. So when we're graphing, if you remember Desmos, let me get back to Desmos. I think I had it open. If I graphed X squared, okay, so this is our function that I'm going to graph, right? So you can see at X is 0, 0 squared is 0. At X is 1, 1 squared is 1. So you can see my point is, here's this point, Oh, no, I don't want to stop. Hang on. Tell you, it's hard when you got to come back to it. Get my pen again. So at 0, 0, right? At when x is 0, y is 0. When x is 1, y is 1. When x is 2, so think 2 squared because that's what our function is, right? And then same thing over here. When x is -1, well, -1 squared is 1. When x is -2, -2 squared is 4. So you can see that algebra says, okay, there's specific points on this specific function. Okay, so now let me go back to clear this. Let me go back to our OneNote. Okay, so we know what the graph looks like, right? So one way to graph quickly, and it's fairly easy to graph quickly, is you set a what's called a T-chart, right? So here's your T-chart. We're going to pick values for x, and it will spit out y values. So that's that idea of a function, right? We put in 0. When I plug 0 into x squared, I get 0 squared is 0. So that's my first point. When I plug in 1, I get 1 squared is 1. So when x is 1, y is 1. When I plug in 2, I get 2 squared, which is 4. So when x is 2, y is 4, right? And then I can go the other way too, even though this one doesn't show it. When x is -1, so remember, -1 squared is -1 times -1, which is +1. So I have a value here. If I went this way and I had -2, -2 would be +4 because -2 squared is +4. So I can graph this fairly easily, right? So I know it's going to be a curve, and it's not going to be curvy that much, but you get the idea. Okay, so there's my graph. And then because it's a parabola, right, it has the same shape on the other side. It's symmetrical. Okay, so we know that those are symmetrical. So what this is saying though is, since we're talking about a limit, so again, read this, the limit as x approaches 3 of the function x squared. So what is the limit? So as you're looking at this, remember we're using our fingers, right? We're bringing our fingers. So think of my left finger is coming up on the left side. So I'm heading towards 3. And then my right side, I'm coming in from the right side. And I am also heading towards x is 3. Well, my fingers are meeting right here, which when I look over here, my limit is 9. Okay, so my fingers are coming up from the right, or I'm sorry, up from the left, down from the right, and my fingers at x is 3 meets where y is 9. Okay, so algebraically, it makes sense, right? When we plug in 3 to our function, 3 squared is 9, right? That's algebraically, it equals 9. But we're not talking about what it equals anymore. We don't care about what it equals. What we care about is what is it approaching, okay? That's the limit. What is it approaching, okay? So I'm going to show you, we're going to talk more about limits graphically, because that to me is the most important part. Algebraically, we put it in, into the function and we figure it out. But what I want you to really get in your mind is, what is the value approaching? And is it approaching from the same, like from the right and the left? Does it approach the same value? So when you look at this, and you'll see this in class, I have fingers. So this one is my left finger, and it's coming in and it's approaching here. This is my right finger, and it's coming in and approaching the point here. So what I'm looking at is the limit as x approaches 0, because this is the x value of 0 of this function. So we'll call it the f function. What is it approaching, right? Where are my fingers gonna touch? Well, on this graph, my finger is gonna touch right at y is 2, right here. So this is my y value. So remember, limit always equals a y value, always. The x value down here is what am I approaching? What on the graph, where is it getting close to? Okay, now, if I erase all this, and let's say I want to go to a different spot. So the limit as x approaches -3 of this function. Okay, so now we don't care about anything over here, right? This doesn't matter. All we care about is what's going on right around this value. Okay, that's what we care about. So I grab my left finger and I come in. It's approaching -2 here. I come in with my right finger. It's approaching -2 here. They are coming together, right? My fingertips are coming together, and it comes together. The graph is about 1 3/4, about. Oh, you know what? Hang on, that's at 2. I'm going to change this. At -2. Okay, so whatever your x value is approaching, that's where you look on the graph. Everything else about the graph you don't care about. You want to focus in that area. Okay, don't let the rest of the graph mess you up. Only look at where the graph is focusing on. Okay, so let me try one more. Oops. Okay, so the limit of my function as x approaches 8. What does that limit equal? Okay, so again, I'm coming in. I come in, I'm following the graph, and 8 is clear out here. Okay, so I really don't care what's going on over here. All I'm looking at is what is my graph doing as I approach it, right? And if this graph kept going, I'll make it keep going. If it kept going and, wound around. And so when I come in from the left, it's approaching this value right here. When I come in from the right, it's also approaching that same value. So what is the y value that I'm approaching? So when x is 8, y is about 0. Okay, so that's the y value is right here. When x is, or when x is 8, y is 0. Okay, now that's when you see a graph and it comes from both sides, right? Now, what if we look at a graph like this? So now it gets more and more complicated. We have a lot more things going on with these graphs. So with this one, if I said, here is +1, right? So if I said the limit as x approaches 1, and we're going to call this the f function, what does the limit approach? Well, we have an open circle at 1. We also have a closed circle at 1. Okay, what it actually equals is the closed circle. That is the algebra question. So an algebra question says, what does it equal when x is 1? The calculus asks, what is it approaching when x is 1? What is the graph approaching? Okay, so the algebra question is going to look like this. If you ever see a question that is in functional notation, f of 1, f of 2, f of 3, that is algebra. What does it equal, right? One answer. There's no guesswork. You just look for the solid line or the solid dot. So at x is 1, it actually equals 1, 2, 3, 4. It equals 4. But what is the graph approaching at x is 1? So when you're looking at that, here I'm approaching from the left. Here I come in and I approach it from the right. Notice I'm not stopping anywhere out here. I'm only stopping when I get to x is 1. And it's approaching the value y is 2. Okay, so big difference. What does it equal, the solid dot, and what is it approaching when you're looking at the actual graph? And so I don't have to have a value there. So that was that comment. There may not be a value there, but it's still approaching that. I can still look and go, oh, there's a lot going on around that value. Okay. And again, all I'm looking at is what is the x approaching, right? I look at where is it, what am I focusing on? I'm focusing right here. I don't have to worry about anything else. Nothing else matters at this point. It's only what is it approaching and what area am I looking at? That's what I'm focused on. Okay. All right. So let's try another one on this particular graph. The limit of the function as x approaches -1. So now we're looking here. Okay. Now we're looking here. So now let me change colors here. Okay, now we want to see in this area. And hopefully you're already seeing a problem. Okay, because when I approach from the left, and I'm approaching where x is -1, you can see that I'm approaching and I'm heading towards y is 2. Okay, and I'm coming in from the left. Where this side, I'm approaching, because there's nothing else down here, right? The graph isn't down here. The graph is up here now from the right. From the right, I'm approaching and I'm heading towards 4. Y is 4. So now I have a problem. So this is where we talk about a right-handed and a left-handed limit. All right. The left-handed limit looks like this. There's a little negative sign behind the number. So this is saying as x approaches -1 from the left, I am heading towards 2. Okay. Then the next question is the limit of the function as x approaches -1 from the right. So from the positive side, that's this side. I'm coming in and I'm heading towards -1, but it's heading towards 4. So this is the problem. Left side is coming in, it heads towards 2. Right side, it's coming in, it heads towards 4. My fingers are not together. Okay, my fingers are not together. That means the limit, as x approaches -1, now there's no sign after it. So that means, where are my fingers heading? Are they coming together? So coming from both sides at the same time. Okay, if they're coming in from both sides at the same time and they touch, then I know that my limit exists. But if they come in and my left side's coming in low and my right side is coming in high, the limit does not exist. Okay, so the only way a limit actually exists is if my fingers touch, if I'm heading towards the exact same value. If ever you're coming in and your fingers are coming into 2 different places, the limit does not exist. DNE is what you can call it, does not exist. Okay, let me show you another one like that. Here we go. So this one, and this one, there's no number there. It's x naught, just means any value we can plug in. If that messes with you, we can plug in any value, say x is 2. So the limit as x approaches 2 from the left, so I'll make a color change here, from the left. So here I go, I'm coming in, I'm following my graph from the left, and it's approaching this value right here. We're going to call this 3. So it equals 3. Okay. The limit of my function as x approaches 2 from the right. So now you see there's no graph here. So from the right, I'm heading on this side. I'm still heading towards the x value of 2, but it's going to come up here, and we're going to call this 7. It's heading towards 7. So from the left, I'm heading towards 3. From the right, I'm heading towards 7. My fingers are not coming together. There's a gap. So what we say is the limit of my function as x approaches 2 from both sides, right? So now it's simultaneous. My fingers have to come together. Since these two values are different, the limit does not exist. Okay, so that's finding limits graphically. So now let's switch back and let's find limits algebraically. So these are just rules of limits. You can look them over. It's easier, much easier just to actually do them instead of try to walk through these. But some of you like to read math, so I threw those in there. So, okay. So here's the bottom line. This is finding limits algebraically. So what we're doing is we really are just trying to find out what's going on our function at a certain value. Okay, so this first one says the limit of this function as x approaches 5, right? Well, graphically, if x is 5, I look up to my graph to see, do my fingers come together, right? What's my graph doing? Well, it's the same idea here. All I have to do is plug the value in. So I take out the x, I plug in 5, take out the x, plug in 5, and now I use order of operations to calculate. 5 squared is 25, times 2 is 50. 8 minus 5 is 40, plus 3. So 50 minus 40 is 10, plus 3 is 13. So the limit as x approaches 5 of this function, it's approaching 13. Just plugged in the values, worked it out. Okay. Number 4, as x approaches 4, what's going on here? So I take out the x, I plug in 4. So the limit as x approaches 4 of 29 minus x is square root of 25 is plus or minus 5. Always plus or minus unless it's very specific. Okay. So it really is plug and chug. You plug in the value, you chug out the answer. All right, now that works great for any polynomial, radical, anything like that. Although keep in mind that with a radical, you can't have a negative underneath it, right? So you have to be careful with that. Remember the other domain restriction. With a fraction, you can't have 0 at the bottom. So you always just plug and chug. Plug in, see if it works out. So the limit as x approaches 4. So I'm going to take out the x and plug in a 4. Take out the x, plug in a 4. So 16 minus 16 is 0. 4 minus 4 is 0. Uh-oh, we have an issue. Red flag, right? Huge red flag. This is no bueno. Can't have that, right? This is called an indeterminate form. 0 over 0. That's not even like does not exist or 0. It's just called an indeterminate form. So what that means is that it needs more work. That's what it means. It means you got to do something else to it, right? There's got to be something else that you got to do. So this is where factoring comes in. So if you remember when I sent out the email for school, I said, make sure you know how to factor because this business calculus class doesn't put any emphasis on factoring, but it shows up periodically throughout the semester. So factoring is a big deal because it will stop you on a dime if you don't know how to factor. Okay, so it will be an issue if you don't know how to factor. Okay, so how do we factor? So remember, I'm not going to go over it, but I have videos that you can watch to remind yourself on how to factor. So this top one is called the difference of two squares. So you can factor where it's x minus 4, x plus 4. So that's the top. And when I divide off the x minus 4 on the bottom, you can see these are the same. So I can cancel those. So it becomes x plus 4. So now I can say, okay, the limit as x approaches 4 of x plus 4 is 4 plus 4 equals 8. That's the limit. Okay, so this whole thing of indeterminate form, what you did just now, when you factor and cancel, you are canceling out that indeterminate form, that 0 over 0. That's what you've done. All right, so anytime you see a fraction, 8 out of 10 times, I'm not going to say 10 out of 10, 8 out of 10 times you have to factor to get it to where you factored out the indeterminate form. Okay, all right, let's try this one. So, fraction, if I plug 2 in here, I get 4 plus 10 is 14 minus 14. That gives me 0. If I plug 2 in here, I get 3 times 2 is 6 minus 6, 0 over 0. So that means I need more work. Okay, so I'm going to factor. So if I factor out a 3 on top, I get x minus 2, so that's that factoring greatest common denominator. Here I have x squared plus 5x minus 14, so this is how I factor these. I get a negative 14 on top, a positive 5. What are the factors of negative 14? So I have 7 times 2. One of them has to be negative. Since my middle number is positive, my smaller number over here has to be negative. So the bigger numbers are going to match. The bigger number is going to match your middle sign. So this one is x plus 7, x minus 2. Oh, there you go. There is your indeterminate form. There's your 0 over 0. So now I have the limit as x approaches 2 of 3 over x plus 7. And now I can plug in chug. So I get 3 over 9, which is 1/3. So that's the limit. Okay, so fractions, 8 or 9 times out of 10, you're going to have to factor. So again, factoring does come in periodically. Okay, all right, so this is the idea of the one-sided limits that we talked about, left side, right side. We already talked about those. So I introduced it, and now we're going to actually see them for what they are. Yeah, we probably should do this one. Okay, let's step back a minute. Let's go ahead and do this one. So this is another plug and chug. Just remember, this is another one of those review things. Fractional exponent. Some people call it rational exponent. I like it fractional because it explains what it is. So when you have a fractional exponent, meaning an exponent that's a fraction, this is just a radical. It's just an easier way to write a radical. So this is how I show it. There's your radical. Here is your radicand. This is the index. Okay, all you're going to do is you're going to take the radicand. This becomes the denominator. The index becomes the denominator. I've seen some people just do this. They just bring the index to underneath. Okay, so if you had, 5th root of x cubed, this would be x to the 3/5. That's what that means. So you want to be able to go back and forth between fractional exponent to a radical back to a fractional exponent. Okay, so that's what we have here. So again, we're just going to plug in. It's not a fraction, so we don't have to worry about indeterminate form. So we're just going to plug in that 36. So 1/2 of 36 minus 36 raised to the 1/2. So 1/2 of 36 is 18. This 36 raised to the 1/2 is the same as the square root of 36. So it's going to be 18 minus 6, which is 12. Yeah, 12. Okay. So that one wasn't too bad. That one just another plug and chug. All right. So now right and left-handed limit. So remember, left-handed is coming in from the negative side. So there's going to be a negative sign after the value. Right-handed limit is coming in from the positive side because it's coming in from the right. So there's going to be a positive value. So with limits, you want to be real specific as to where are you looking, right? So when you look at these, you're looking at +2. So we are looking right in this area. We don't care about anything over here. We don't care about anything over here. All we care about is what's going on right at these values. Okay, so we look at this and we go, okay, it's as x approaches 2 from the left. Okay, so we look here, we're approaching 2 from the left, and it's heading towards 1. Here, x is approaching 2 from the right. So we come in from the right, and it's heading towards 2. These are not the same. Okay. C is saying, what is it heading towards when I come in simultaneously? In other words, are my fingers going to touch? Well, when you look at this, you can see there's a big gap between 1 and 2. So since these are different, the limit does not exist. Okay, so right-handed limit, left-handed limit. Okay. If they are not the same, the limit does not exist. Now, if they come and they both go to the same place, then that's what the limit is. That limit does exist at that place. Okay. Okay, so for this one now, so this is graphically, right? Example 8 is graphically, being able to find limits right-handed, left-handed graphically. Now we're going to look at it algebraically, right and left-handed limit algebraically. So when you look at x is less than or equal to 4. So if you look at this graphic with a number line, that x is less than or equal to 4 looks like this, right? It's all the values less than or equal to 4. If I have x is greater than 4, it doesn't equal 4, but it's everything bigger than 4. Okay, so that's the difference between those two. So when you look at A, it says x is approaching 4 from the left. Well, this one here, the second one, there's nothing going on from the left. This one says it starts at 4 and goes higher. This one, the first one says, oh, it's only values that are to the left of 4. So what that tells you is you can only use this one for A. Because this one, the second one, there is no values to the left of 4. The only values left of 4 is x minus 5. So you can rewrite this as the limit as x approaches 4 from the left of x minus 5. And then again, it's just a plug and chug. So 4 minus 5 is -1. Okay, so that what this does, the right and the left hand, it is determined by the inequality symbol. So if you have a less than sign, this is a left-handed limit. A greater than sign, so this is less than, greater than. This is a right-handed limit. So it kind of tells you which one to use, which function to use. So B says we're approaching 4 from the right. Well, again, going back to our little line graphs here, The only one that has a value that is greater than 4 is x is greater than 4. So we have to use this bottom one. So the limit of 3x minus 4 as x approaches 4 from the right. So again, you plug in chug. 3 times 4 minus 4. So 12 minus 4 is 8. So this one approaching from the left is -1. This one approaching from the right is 8, which means C says we're coming in both fingers. Well, they are not coming to the same place. From the left, it's heading towards -1. From the right, it's heading towards 8. So that automatically tells you that this one does not exist. Okay, even though you have an equal sign, you have that x is less than or equal to 4, that doesn't matter. What matters is, what are we approaching? And are we approaching the exact same value? Okay. All right, that's it for introduction to limits. Okay, I'm going to stop there. Please make sure that you take a look at your schedule for any tutoring that you need. There's the 2 different math labs. Math lab in JH308 is one-on-one. JH316, you can go in and there's tutors wandering around. You can sit and do your homework, raise your hand, and they will come and help you. Make sure they've taken business calculus, though. Sometimes that is an issue. So anyway, okay, I will see you later. If you're watching this, I'm probably on a plane to Ireland.